J.J. Thomson's experiments with the discharge tube with different gases filled in it, one at a time, led to the conclusion that all the elements contain negatively charged particles, which were later called electrons. Since the atom is electrically neutral, it was proposed that the atom must also contain positively charged particles in it, such that the total negative charge in the atom is equal to the positive charge in it. Based on these assumptions, J.J. Thomson proposed the plum pudding model of the atom. In this model, he proposed that the total positive charge in the atom is spread throughout its volume, and the negatively charged electrons are distributed in this volume like seeds in a watermelon. But subsequently, an experiment proposed by Ernst Rutherford and carried out by his students Hans Geiger and Ernst Marsden to understand the structure of the atom proved that the plum pudding model of the atom was not in agreement with the results of the experiment. Rutherford proposed that the scattering of the alpha particles from atoms of an element would be helpful in understanding the structure of the atom. Let us now study and understand the Rutherford's alpha particle scattering experiment, which led to Rutherford's nuclear model of the atom. The experimental setup consisted of a source of alpha particles, like bismuth-214, placed in a cavity in a lead block, and the arrangement was made to obtain a narrow beam of alpha particles by passing them through space between lead bricks. Here, we should remember that the alpha particles were actually helium nuclei. As we know, the charge of the alpha particle is 2 times the charge of the proton, and its mass is 4 units. The narrow beam of alpha particles so obtained was allowed to fall on thin gold foil of thickness around 2.1 into 10 to the power minus 7 meter, that is 0.21 micrometer. The scattered alpha particles were made incident on a zinc sulfide screen. The zinc sulfide screen being a fluorescent screen, the alpha particles upon striking the screen caused scintillations leading to the detection of their presence. The scintillations were observed through a microscope. This entire arrangement was enclosed in a vacuum chamber to avoid stray particles, if any, entering the experimental area. It was observed experimentally that most of the particles passed off straight through the gold foil without any deviation in their path. A few of them suffered minor deviations, and very few of them suffered large deviations. These deviated particles were studied as a function of the angle of scattering. Angle of scattering is defined as the angle between the path of incident particle on the gold foil and the path of the scattered particle away from the gold foil. A graph was plotted between the number of scattered particles detected on the y-axis and the scattering angle on the x-axis. Based on the data from the graph, Rutherford made the following conclusions. The number of particles for nearly zero angle of scattering was very large, indicating that most of them had passed almost straight through the gold foil. This implied that most of the atoms must have been empty. Out of all the incident alpha particles, only about 0.14% of the particles scattered by more than 1 degree. This was due to the fact that these particles passed close to the central part of the atom, which must have been positively charged. And 1 in 8,000, that is about 0.0125% of the incident alpha particles scattered by more than 90 degrees, that is, they scattered backwards. For this to have happened, such alpha particles must have experienced a large repulsive force. This would be possible only if most of the atom was empty and its entire positive charge was concentrated tightly at the central part called the nucleus. In such a case, the alpha particles which moved very close to the central part would experience large repulsive forces and suffer deflections greater than 90 degrees. Based on these assumptions, Rutherford proposed the atomic model, henceforth called the Rutherford's nuclear model of atom. The entire positive charge and most of the mass of the atom is concentrated at the center of the atom called the nucleus. He also proposed that the electrons revolved around the nucleus in orbits, just like planets revolving around the sun. Hence, the Rutherford's atomic model is also known as the planetary model of the atom. Based on Rutherford's experiments, the size of the nucleus was estimated to be around 10 to the power minus 15 meter to 10 to the power minus 14 meter. According to the kinetic theory of gases, we know that the size of atom is about 10 to the power minus 10 meter. So, the atom is about 10,000 to 100,000 times larger than its nucleus. Now, by using Rutherford's nuclear model of the atom, we can explain the scattering of alpha particles from the gold foil. As the gold foil is very thin, it can be assumed that the alpha particle undergoes one scattering due to the gold nucleus. So, to calculate the trajectory of an alpha particle, it is enough to consider the scattering of an alpha particle by a single gold nucleus. The atomic number of gold is 79. That is, the nucleus of gold contains 79 protons. Therefore, the charge on the gold nucleus is equal to 79e, where E is assumed to be the charge on each proton. Hence, the gold nucleus is approximately 50 times heavier than the alpha particle. Hence, it can be assumed that the gold nucleus remains stationary during the scattering process. Now, according to Coulomb's inverse square law of electrostatics, the magnitude of the repulsive force between the alpha particle and the gold nucleus F is equal to 1 by 4 pi epsilon naught into 2e into Ze by r square, where r is the distance between the alpha particle and the nucleus of the gold atom. This force acts along the line joining the alpha particle and the nucleus of the gold atom. The direction of this force and its magnitude continuously changes as the alpha particle approaches or recedes from the nucleus. The path of the alpha particle depends on the impact parameter b for the scattering, which is defined as the perpendicular distance between the direction of the initial velocity of the alpha particle and the nucleus of the gold atom. The alpha particles have a range of impact parameters. So the alpha particles are scattered in different directions. If the impact parameter is large, the alpha particles pass without deviation. That is, the scattering angle is approximately 0 degrees. For relatively small values of b, that is, when the alpha particles are directed very close to the nucleus, there are huge deviations. If the alpha particles are directed in the same line as of the gold nucleus, then they undergo a head-on collision, in which case the impact parameter is the least and hence the scattering angle is approximately 180 degrees. Therefore, such alpha particles bounce back. Since very few of the incident alpha particles undergo head-on collision, it can be said that the mass of the gold atom is concentrated in a very small region called the nucleus. According to the Rutherford model of the atom is electrically neutral. It was proposed by the Rutherford model of the atom that the centripetal force Fc on the revolving electrons was provided by the Coulomb force Fe of attraction between the electron and the nucleus to keep them in their orbits. Let us apply this concept to the case of a hydrogen atom. A hydrogen atom consists of one electron revolving around its nucleus, which is actually the proton. For the electron revolving with speed v, the centripetal force Fc is equal to mv square by r. The electrostatic force of attraction Fe between the electron and the proton in the nucleus of the hydrogen atom, separated by a distance r, is given by Fe is equal to 1 by 4 pi epsilon naught into E square by r square. This is true because the proton and the electron have equal magnitude of charge E on them. But for dynamically stable orbits, Fc is equal to the electrostatic force Fe. Hence, mv square by r is equal to 1 by 4 pi epsilon naught into E square by r square. Let this be equation 1. On simplifying equation 1, we get the radius r is equal to E square by 4 pi epsilon naught mv square. Let this be equation 2. From equation 1, we also have v square is equal to E square by 4 pi epsilon naught mr. Let this be equation 3. The kinetic energy of the electron in the hydrogen atom is K and is equal to half mv square. Substituting v square in the expression for kinetic energy, we get K is equal to E square by 8 pi epsilon naught r. Let this be equation 4. The electrostatic potential energy of the electron, U, is equal to minus E square by 4 pi epsilon naught r. Let this be equation 5. The total energy of E of the electron in the hydrogen atom is equal to the sum of the kinetic energy K and the potential energy of the electron U. By substituting the expressions for K and U and simplifying, we get E is equal to minus E square by 8 pi epsilon naught r. So, the total energy of the electron is negative. This implies that the electron is bounded to the nucleus. When a metallic body is heated, it emits electromagnetic radiation. The radiation may consist of different wavelengths. The electromagnetic radiation may consist of different components having different wavelengths. For example, when the filament of an electric bulb is heated, it emits white light consisting of radiations in the visible range. When this white light is passed through a prism, we obtain a continuous spectrum consisting of all the wavelengths in the spectrum. This spectrum appears as bright lines where one color gradually merges into the other, without a clear demarcation between the adjacent colors. Similarly, when hydrogen gas, which is enclosed in a sealed tube, is heated to high temperatures, it emits radiation. When this radiation is passed through a prism, we obtain the hydrogen spectrum. This spectrum is not a continuous spectrum. It consists of some sharply defined discrete wavelengths. For example, the spectrum consists of light of wavelengths 6563 angstrom and 4861 angstrom in the visible region. A hydrogen sample also emits radiation with wavelengths greater than those in the visible region. Thus, the spectrum emitted by the hydrogen atom is a discontinuous emission line spectrum as it contains only specific wavelengths of light. When an atomic gas or vapor is excited at a low pressure, by passing electric current through it, it emits radiations containing certain specific wavelengths only. Such a spectrum is called the discontinuous emission line spectrum. The line spectrum is characteristic of the element emitting it. This means that no two elements can give the same line spectrum. Hence, it is also called as the fingerprint spectrum. An emission line spectrum consists of bright lines on a dark background. Now let us again look at the hydrogen spectrum, which was discussed earlier. In the spectrum emitted by the hydrogen atom, the spectral lines can be grouped in separate series. In each series, we observe that separation between successive wavelengths decreases as we go from the higher wavelengths towards the lower wavelengths. Each such set is called a spectral series. An important point to remember is that the wavelengths in each series approach a limiting value known as the series limit. Johann Jacob Balmer was the first to observe such a spectral series. Hence it was named as the Balmer series. The other such series emitted by hydrogen are namely the Lyman series, Paschen series, Brackett series, and Pfund series, where each one has been named after its discoverer. Let us look at the lines emitted as part of the Balmer series. The line with largest wavelength in the series is called H alpha, then followed by H beta, H gamma, and so on, in the descending order of wavelengths. As the wavelength decreases, the lines appear closer and weaker in intensity. The Balmer series lies in the visible region. Now, let us look at the H alpha line of the Balmer series. Balmer gave a simple empirical formula which these wavelengths follow. If the wavelength of the spectral line emitted is lambda, then 1 by lambda is equal to r into 1 by 2 square minus 1 by n square, where r stands for Rydberg constant, which is equal to 1.097 into 10 power 7 per meter, and n takes integral values 3, 4, 5, and so on up to infinity. This equation is called the Balmer formula. Let this be equation 1. Balmer series can also be written in terms of frequency, nu. We know that velocity of light c is equal to nu lambda. That implies 1 by lambda is equal to nu by c. Substituting this value of 1 by lambda in equation 1, we get nu is equal to rc into 1 by 2 square minus 1 by n square. Substituting n equal to 3 in equation 1, we get 1 by lambda is equal to 1.097 into 10 raised to the power 7 into 1 by 2 square minus 1 by 3 square. This is equal to 1.522 into 10 raised to the power 6. Thus, lambda is equal to 6563 angstrom or 656.3 nanometer. This is the wavelength of the H alpha line of the Balmer series in the red of the visible region. For the next line of the series, the H beta line, we have n equal to 4, and for n equal to 5, we obtain the H gamma line of the series. By putting n equal to infinity, we obtain the limiting wavelength of the series, which is equal to 3646 angstrom or 364.6 nanometer. The limiting wavelength is the shortest wavelength of the series. Now let us look at the Lyman series, which has wavelengths in the ultraviolet region of the spectrum. The presence of ultraviolet wavelengths can be detected by a silver chloride soaked paper, which turns black when exposed to them. The empirical formula for the Lyman series is 1 by lambda is equal to R into 1 by 1 square minus 1 by n square. Here, n is equal to 2, 3, 4, and so on, up to infinity. Let this be equation number 2. Now let us look at the Paschen series. The Paschen series has spectral lines which lie in the infrared region. The formula for the Paschen series is 1 by lambda is equal to R into 1 by 3 square minus 1 by n square. Here, n is equal to 4, 5, 6, and so on, up to infinity. Let this be equation 3. The bracket series has spectral lines which lie in infrared region. The formula for the bracket series is 1 by lambda is equal to R into 1 by 4 square minus 1 by n square. Here, n is equal to 5, 6, 7, and so on, up to infinity. Let this be equation 4. The Fun series has spectral lines which lie in infrared region. The formula for the Fun series is 1 by lambda is equal to R into 1 by 5 square minus 1 by n square. Here, n is equal to 6, 7, 8, and so on, up to infinity. Let this be equation 5. Spectra of only few elements like hydrogen, singly ionized helium, doubly ionized lithium, etc. can be represented by the simple formulae like equation 1, 2, 3, 4, and 5. Still, these equations are very important as they give the wavelengths that a hydrogen atom radiates or absorbs. When white light passes through a gas and the transmitted light is analyzed, we get a spectrum called absorption spectrum. The absorption spectrum consists of dark lines corresponding to the wavelengths which were formed in the emission spectrum of the same gas. An element can absorb those wavelengths which it can emit. The absorption spectra of elements consists of dark lines against a bright background. Rutherford's nuclear model of the atom postulates that electrons revolve around the nucleus, which contains the total positive charge of the atom. However, it could not explain certain other facts. Let us now look into the drawbacks of Rutherford's atomic model. It assumes that the system of electrons revolving around the nucleus is similar to that of our planetary system. As the gravitational force holds the planetary system together, the electrons around the nucleus are held by electrostatic force in an atom, which is given by Coulomb's law. The electrostatic force between the electron and the nucleus acts as the centripetal force on the electron, because of which the electron gains centripetal acceleration. According to the classical electromagnetic theory, an accelerated electron should continuously lose energy as it emits radiation in the form of electromagnetic waves. As a result, the electron would spiral inward and eventually fall into the nucleus, and thus make the atom unstable. Also, the classical electromagnetic theory states that the frequency of electromagnetic waves emitted by the revolving electrons is equal to the frequency of its revolution. As an electron spirals inward, its angular velocity and frequency changes continuously, which consequently changes the frequency of the emitted radiation to form continuous spectra. But experimentally, a line spectrum is observed. The hydrogen spectrum is an experimental evidence for the above analysis. So it is clear that the classical electromagnetic theory and Rutherford's atomic model were inadequate to explain the atomic structure. In order to overcome these limitations, in 1913, Niels Bohr gave his postulates based on quantum theory of radiation. He combined the concepts of the classical and quantum theories to form the basis of his three postulates of an atomic model. According to the first postulate, an electron in an atom could revolve in certain stable orbits without losing energy continuously. This means each atom exists in a definite stable state, and each existing state has a definite total energy. These are called the stationary states of the atom. Therefore, as long as the electron occupies these stable states, there is no loss of energy in the electron. According to Bohr's second postulate, the electron revolves around the nucleus only in those orbits for which the angular momentum L is an integral multiple of a constant equal to nh by 2 pi, where h is Planck's constant equal to 6.625 into 10 to the power minus 34 joule second. Therefore, the angular momentum L of the electron is equal to mvr, which is equal to nh by 2 pi, where m is the mass of the electron, v is its velocity, r is the radius of its revolving orbit, and n is an integer. Let this be equation 1. According to Bohr's third postulate, an electron might make a transition from one specific non-radiating orbit to another of lower energy. When it does so, a photon is emitted having energy equal to that of the energy difference between the initial and final states. Then, the frequency nu of the emitted photon is given by the relation h nu is equal to EI minus EF. Here, EI is the initial state energy and EF is the final state energy of the electron. Let this be equation 2. Let us now derive the expression for the radius and energy of the hydrogen atom. From equation 1, we can write mvnRn is equal to nh by 2 pi. Here, n is an integer, Rn is the radius of nth possible orbit, and Vn is the velocity of the electron in the nth orbit. Let this be equation 3. The allowed orbits are numbered 1, 2, 3, and so on, according to the values of n, which is called the principal quantum number of the orbit. We have learned that the relation between the radius r of the electron orbit and its corresponding velocity v is given by Rn is equal to E square by 4 pi epsilon naught mvn square. Let this be equation 4. Substituting the value of Rn in equation 3 and simplifying, we have Vn is equal to E square by 2 epsilon naught NH. Let this be equation 5. Substituting equation 5 in 3 and simplifying, we get Rn is equal to epsilon naught N square H square by pi Me square. Let this be equation 6. By substituting n equal to 1 in the above equation, we get the radius of the innermost orbit, which is Bohr's orbit and is represented by A0. Given A0 is equal to epsilon naught H square by pi Me square. Substituting the value of Planck's constant H, epsilon naught and the magnitude of the charge of the electron E, and simplifying, we get A0 is equal to 0.529 into 10 to the power minus 10 meter, which is equal to 0.529 angstrom. From equation 6, it is clear that the radii of orbits are directly proportional to n square. According to Rutherford's model of the atom, the energy En of an electron for a particular orbit of radius Rn is equal to minus E square by 8 pi epsilon naught Rn, where n is the principal quantum number. Let this be equation 7. Substituting the value of Rn and simplifying, we get En is equal to minus me to the power 4 by 8 n square h square epsilon naught square. Let this be equation 8. Substituting the values of m, e, epsilon naught, h and simplifying, we get En is equal to minus 13.6 by n square electron volt. Let this be equation 9. The negative sign of the total energy of an electron moving in an orbit means that the electron is bound with the nucleus. Substituting n equal to 1 in equation 9, we get the energy of the first orbit, E1, is equal to minus 13.6 electron volts. This is the lowest energy state of the atom and is called the ground state. Thus, the minimum energy required to remove the electron from the ground state is 13.6 electron volts. This is called the ionization energy of hydrogen atom. When an electron gains enough energy to go to higher orbits, the atom is said to be in an excited state. By substituting n is equal to 2 in equation 9, we get the energy of the second orbit, E2, as minus 3.4 electron volts. Similarly, by substituting n is equal to 3 in the expression for En, we get the energy of the third orbit, E3, as minus 1.51 electron volts. So, to excite an hydrogen atom from ground state, where n is equal to 1, to the first excited state, where n is equal to 2, the energy required is E2 minus E1. This is equal to minus 3.4 of minus 13.6, which is equal to 10.2 electron volts. Similarly, to excite an hydrogen atom from the ground state, where n is equal to 1, to its second excited state, where n is equal to 3, the energy required is E3 minus E1. This is equal to minus 1.51 minus 13.6, which is equal to 12.09 electron volts. When the electron falls from the excited state to its ground state, it emits a photon whose energy is equal to the energy difference between the excited state and the ground state. For example, if the electron comes to its ground state from the first excited state, the energy difference will be E2 minus E1 equal to 10.2 electron volts. And thus, a photon of energy 10.2 electron volts will be emitted. We can observe the various energy states of hydrogen atom in the form of an energy level diagram as shown. In this diagram, the 0 electron volts corresponds to an energy of N equal to infinity, which is the highest energy state. This is the energy when the electron is completely removed from the atom and is at rest. The line spectra of the hydrogen atom was explained by the third postulate of Niels Bohr. We know that when an electron in a lower energy level with principal quantum number N1 absorbs energy from a photon, it jumps to a higher energy level, such that the photon energy will be equal to E2 minus E1, where E2 is the energy of the level corresponding to N2 and E1 is the energy corresponding to N1. Similarly, when an atom jumps from a higher energy level, E2, to a lower energy level with energy E1, a photon is released with the frequency nu, such that H nu is equal to E2 minus E1. Let this be equation 1. We have seen from Bohr's postulates that the energy En of any level corresponding to a principal quantum number n is given as En equal to minus m e to the power 4 by 8n square epsilon naught square h square. Now using the result of equation 2 for N1, the energy E1 is equal to minus m e power 4 by 8 n1 square epsilon naught square h square. Let this be equation 3. Similarly, for N2, the energy E2 is equal to minus m e to the power 4 by 8 n2 square epsilon naught square h square. Let this be equation 4. On substituting equations 3 and 4 in equation 1 and simplifying, we get h nu is equal to m e to the power 4 by 8 epsilon naught square h square into 1 by n1 square minus 1 by n2 square. This equation is called Rydberg's formula. Let this be equation 5. From equation 5, we get nu is equal to m e to the power 4 by 8 epsilon naught square h cube into 1 by n1 square minus 1 by n2 square. Let this be equation 6. Substituting n1 is equal to 2 and n2 is equal to 3 in equation 6, we get nu is equal to m e to the power 4 by 8 epsilon naught square h cube into 1 by 2 square minus 1. From equation 6, comparing nu with the empirical formula for Balmer's series that you have learnt earlier, we get nu is equal to Rc into 1 by 2 square minus 1 by n square. Hence, we see that the value of R, or the Rydberg's constant, is equal to m into e to the power 4 by 8 epsilon naught square h cube c. Substituting the values of mass of the electron m, charge on the electron e, permittivity of free space epsilon naught, Planck's constant h, and speed of light c, we get r is equal to 1.03 into 10 to the power minus 7 per meter. This value of r is very close to 1.097 into 10 to the power minus 7 per meter, which is obtained from the empirical formula of Balmer. This agreement between the theoretical and experimental values of Rydberg's constant provided a direct and striking confirmation of the Bohr's model of the atom. So, when we substitute N1 is equal to 2 and N2 is equal to 3, 4, 5 and so on, we get the Balmer series. Similarly, when we take N1 is equal to 1 and N2 is equal to 2, 3, 4 and so on, we get the Lyman series. When N1 is equal to 3 and N2 is equal to 4, 5, 6 and so on, we get the Paschen series. When N1 is equal to 4 and N2 is equal to 5, 6, 7 and so on, we get the bracket series. Similarly, when N1 is equal to 5 and N2 is equal to 6, 7, 8 and so on, we get the Pfund series. In this diagram, it is clearly seen how different atomic series are produced when electrons jump from a state of higher energy to a lower one. These lines are called emission lines. Likewise, absorption spectra is also obtained when an atom absorbs a photon having an energy equal to the difference in energies of two levels, and it makes a transition from the lower energy level to the higher one. This is called absorption. Thus, if photons having a continuous range of frequencies pass through a rarefied gas and then are analyzed with the spectrometer, a series of dark spectral absorption lines appear in the continuous spectrum. These dark lines indicate the frequencies that have been absorbed by the atoms of the gas from the incident photons. Thus, Bohr's model was successful in explaining the hydrogen atom spectra. But Bohr's second postulate was a puzzle for 10 years, till Louis de Broglie explained it in 1923. Until then, no one could explain why the angular momentum should be an integral multiple of h by 2 pi. We have learned from Davison-Germa's experiment that material particles like electrons, protons, neutrons, etc. possess a wave nature, which was actually proposed by de Broglie. Let us now understand how de Broglie explained Bohr's second postulate. When a string is plucked, a large number of wavelengths are produced, but only those wavelengths survive which have nodes at the ends and form standing waves along the string. Thus, standing waves are formed only when the total distance travelled by the wave in a to and fro direction is equal to one wavelength, two wavelengths, or any integral number of wavelengths. Now, let us apply this concept to an electron in the nth circular orbit of radius Rn. The total distance travelled by the electron is 2 pi Rn. Hence, 2 pi Rn is equal to n lambda, where n is equal to 1, 2, 3, and so on. Let this be equation 7. We know that de Broglie's wavelength corresponding to the motion of a particle having a momentum p is given by lambda is equal to h by p. Here, h is the Planck's constant and p is its momentum. As momentum is the product of the mass m and the velocity v, we have lambda is equal to h by mvn. Here, Vn is the velocity of the electron in the nth orbit. Substituting the value of lambda in equation 7, we have 2 pi Rn is equal to nh by mvn. Rearranging the equation, we get mvn Rn is equal to nh by 2 pi. Let this be equation 8. Thus, the angular momentum of an electron is quantized. The quantized electron orbits and energies are due to the wave nature of the electron. Equation 8 is nothing but Bohr's second postulate. In spite of the amazing results of Bohr's model, it had some drawbacks. Bohr's model could be applied only to hydrogen-like atoms. That is, the atoms having only one electron, like singly ionized helium, doubly ionized lithium, etc. It could not explain the spectrum of atoms with more than one electron. Bohr's model included only the electric force between the electron and nucleus, but it did not take into consideration the electric forces between electrons in multi-electron atoms. Though the frequency of spectral lines was correctly predicted by Bohr's model, some frequencies are relatively more intense than the others. Bohr's model could not explain this fact. Thus, the atomic model of multi-electron atoms can be better understood by applying a new theory called the quantum theory.